In hospitals, the power source for lighting must be capable of supplying both normal and emergency lighting. Branch circuit sizes are typically based on the lighting connected to the circuit. For the portion of the lighting load on a critical branch panel, the normal lighting load may be reduced by an amount equal to the emergency lighting load on the same circuit. This is addressed in Article 220.52 of the National Electrical Code. To elaborate on this, it is essential to understand how to apply these principles in practical scenarios. Suppose a hospital requires 2 volt amps per square foot for lighting load. However, less than half of the lighting is connected to the critical branch. In such a case, you can use 1 volt amp per square foot for the critical branch, assuming that the remaining 1 volt amp per square foot is provided by the normal panel. This approach ensures that the critical branch is adequately powered for emergency lighting while optimizing the load distribution between the normal and critical panels. The proper application of Article 220.52 allows for a more efficient and accurate calculation of the load on the critical branch panel. It prevents oversizing the critical branch panel, which can lead to unnecessary costs and inefficiencies. Furthermore, it ensures that the normal panel is appropriately sized to handle the remaining lighting load. To illustrate this further, consider a specific example. Imagine a hospital wing with a total area of 10,000 square feet. According to the NEC, the total lighting load would be 2 volt amps per square foot, resulting in a total lighting load of 20,000 volt amps. However, if only 40% of the lighting is connected to the critical branch, the critical branch load would be 4,000 square feet times 2 volt amps per square foot, equaling 8,000 volt amps. Applying Article 220.52, you can reduce the normal lighting load by the amount of emergency lighting load on the same circuit. If the emergency lighting load is, for instance, 1 volt amp per square foot, the critical branch load would be calculated as 4,000 square feet times 1 volt amp per square foot, resulting in 4,000 volt amps. The remaining 4,000 square feet would be powered by the normal panel, contributing the remaining 4,000 volt amps to the overall lighting load. This methodology ensures that the critical branch panel is sized appropriately for its intended purpose, providing essential emergency lighting while optimizing the load distribution between the normal and critical panels. The importance of adhering to Article 220.52 lies in its ability to balance the need for emergency lighting with the efficient use of electrical resources. By reducing the normal lighting load by an amount equal to the emergency lighting load in the same circuit, the critical branch panel is not burdened with unnecessary capacity. This approach also helps to minimize the risk of overloading the normal panel, which could lead to power outages and disruptions in hospital operations. Additionally, it is crucial to consider the specific types of lighting fixtures used in the hospital when calculating the load on the critical branch panel. Different types of lighting fixtures have different power requirements, which can affect the overall load calculation. For instance, LED lighting fixtures are typically more energy efficient than traditional fluorescent or incandescent fixtures. Therefore, using LED lighting fixtures can help to reduce the overall lighting load and minimize the size of the critical branch panel. Furthermore, it is essential to account for any other loads that may be connected to the critical branch panel, such as medical equipment or life support systems. These loads must be factored into the load calculation to ensure that the critical branch panel is adequately sized to handle all essential equipment during a power outage. In addition to Article 220.52, other relevant sections of the National Electrical Code may apply to the calculation of the load on a critical branch panel. For example, Article 517 addresses the specific requirements for healthcare facilities, including hospitals. This article provides detailed guidance on the design and installation of electrical systems in healthcare facilities, ensuring that they meet the highest standards of safety and reliability. Moreover, it is important to consult with a qualified electrical engineer or contractor to ensure that the load calculation is performed accurately and in accordance with all applicable codes and regulations. These professionals have the expertise and experience necessary to properly assess the electrical needs of a hospital and design an electrical system that meets those needs safely and efficiently. Remember to keep detailed records of all load calculations and electrical system designs. These records can be invaluable for future maintenance and troubleshooting efforts, as well as for any future expansions or renovations of the hospital facility. Also, periodically review and update the load calculations to account for any changes in the hospital's electrical needs. This will help to ensure that the electrical system continues to meet the hospital's requirements and operates safely and efficiently. Let's delve further into the specifics of Article 220.52 and its practical applications within a hospital setting. This section of the NEC primarily addresses the calculation of feeder and service loads for healthcare facilities, and it is crucial for understanding how to appropriately size the electrical infrastructure supporting critical patient care areas. The core principle of Article 220.52, as it relates to critical branch panels, is the allowance for reducing the normal lighting load based on the presence of emergency lighting on the same circuit. This reduction is permissible because the NEC recognizes that during a power outage, the normal lighting will be automatically switched off, and the emergency lighting will take over. Therefore, the feeder or service supplying the critical branch panel does not need to be sized to accommodate the full load of both normal and emergency lighting simultaneously. To illustrate this concept with a more detailed example, let's consider a surgical suite within a hospital. This surgical suite is 1,000 square feet in size and is required to have a lighting load of 2 volt amps per square foot according to the NEC. This would result in a total lighting load of 2,000 volt amps for the surgical suite. However, let's assume that 50% of the lighting in the surgical suite is connected to the critical branch panel and is designated as emergency lighting. This means that 500 square feet of the surgical suite is powered by the critical branch for lighting, resulting in a potential load of 1,000 volt amps 500 square feet times 2 volt amps per square foot. Now, applying Article 220.52, we can reduce the normal lighting load in the critical branch panel by the amount of emergency lighting load in the same circuit. If the emergency lighting load is also 1 volt amp per square foot, then the critical branch load would be calculated as 500 square feet times 1 volt amp per square foot, resulting in 500 volt amps. The remaining 500 square feet of normal lighting would be powered by the normal panel, contributing the remaining 500 volt amps to the overall lighting load. This calculation demonstrates how Article 220.52 allows for a significant reduction in the size of the critical branch panel, which can lead to cost savings and improved efficiency. It also highlights the importance of carefully planning the distribution of lighting between the normal and critical branch panels to optimize the load distribution. In addition to the lighting load, it is essential to consider other loads that may be connected to the critical branch panel, such as medical equipment and life support systems. These loads must be factored into the load calculation to ensure that the critical branch panel is adequately sized to handle all essential equipment during a power outage. For example, a surgical suite may have equipment such as operating room lights, anesthesia machines, and patient monitoring systems connected to the critical branch panel. Each of these devices will have a specific power consumption, which must be added to the lighting load to determine the total load in the critical branch panel. Furthermore, it is important to consider the diversity factor of the loads connected to the critical branch panel. The diversity factor is a percentage that represents the likelihood that all of the loads will be operating at their maximum power consumption simultaneously. In a hospital setting, the diversity factor is typically lower than in other types of facilities because many of the loads are essential for patient care and must be available at all times. However, it is still important to consider the diversity factor to avoid oversizing the critical branch panel. Another important consideration when calculating the load on a critical branch panel is the voltage drop. Voltage drop is the reduction in voltage that occurs as electricity flows through a conductor. Excessive voltage drop can cause equipment to malfunction or fail to operate properly. Therefore, it is essential to ensure that the voltage drop on the critical branch panel is within acceptable limits. To minimize voltage drop, it is important to use appropriately sized conductors and to keep the length of the conductors as short as possible. It is also important to consider the impedance of the conductors, which is a measure of their resistance to the flow of electricity. Conductors with lower impedance will have lower voltage drop. In addition to these technical considerations, it is also important to comply with all applicable codes and regulations when designing and installing a critical branch panel. The National Electrical Code (NEC) provides detailed requirements for electrical systems in healthcare facilities, including hospitals. These requirements are designed to ensure the safety and reliability of electrical systems in these critical environments. Furthermore, it is important to consult with a qualified electrical engineer or contractor to ensure that the critical branch panel is designed and installed in accordance with all applicable codes and regulations. These professionals have the expertise and experience necessary to properly assess the electrical needs of a hospital and design an electrical system that meets those needs safely and efficiently. In summary, calculating the load on a critical branch panel in a hospital requires a careful consideration of several factors, including the lighting load, other loads connected to the panel, the diversity factor, the voltage drop, and all applicable codes and regulations. By following these guidelines, you can ensure that the critical branch panel is adequately sized to handle all essential equipment during a power outage and that the electrical system operates safely and reliably. The electrical safety of patients and staff in a hospital depends on the proper design and installation of the electrical system, including the critical branch panel.